Yeah, hello guys. So in today's video session, we will discuss regarding the computational models in embedded system, embedded design. However, two designs what we are going to implement in the embedded design has been already been discussed in the previous video or in the previous session. However, we'll recall them back in this particular session. So we were basically looking into the co-design process. Co-design process in the sense we were looking into the process in which I could design the embedded system which is made up of hardware and software components together. And during the architecture process, we were trying to segregate it. So basically, we were looking into the co-design. And in the co-design process, the initial thing what we checked out was what are the fundamental issues that normally a manufacturer or a designer will be facing when he is going to manufacture an embedded system using a co-design process or using a novel process. After this particular issues were all known by us, we are moving forward to know regarding the what are the various models that will be employed in the design of an embedded system. So when coming to the models, I had already told you it's one of the difficult tasks to do, or it's one of the difficult calls to take when I need to select a model for my embedded system. However you select a model for the design of an embedded system, you will keep on, or the designer will keep on changing that particular model based on his requirement or based on his application or based on his functionality as he goes on developing the model before he reaches the end product of that particular system. So the various models what normally a designer will employ has been shortlisted here. The first one is called as DFG model, second one is called as CDFG model, third one is state machine model, or you can also call this particular model as finite state machine model. The fourth one is sequential program model. Sequential program model is all about how you or how a normal software developer is going to write a program. It's in the same manner. Fifth one is concurrent bar communicating process model, where actually the entire task will be split up into small components and you are going to interconnect them. And the last one is called as object oriented model, where the task what your embedded system has to perform will be divided into various objects, and these objects will be interlinked using classes. So we need to study all these particular 6 models in detail. So moving to the very first model, which is called as data flow graph model or data flow diagram model. So basically what this model does is this will be translating the data processing requirement. So when I speak about data processing requirement, this is about the functional requirements what the consumer will be telling the manufacturer. So this will basically be translating the requirements of the user into the data flow graph. So data flow graph is nothing but a data driven model. Data driven model means in the sense it will take care of what are the different inputs, and the inputs are all predetermined or they are all pre-generated in the model, and they are given to the particular blocks in order to generate the required input. In fact, if I explain about all these things here, or if I go with the theory part here, it is very difficult to understand because it is necessary to know how basically this model will be looking like. So if I go with the model, this is how it is going to look like. This is how a data flow model is going to look like. So ultimately what I need is, I need an output y is equal to x minus c, where x is equal to a plus b. So basically a and b are the input, c is the input. So all these inputs are predetermined or they are pre-generated, and they are given to the functional blocks or they are given to the data flow node, what we call them in case of your DFG model, and the required output is generated. So this is the output. This output acts as an input to the second data flow node, where you get one more input c, and the required operation is performed here and you get the required output. So in the data flow model, the data path is the data flow path from input to output. You can call this as an acyclic data flow model because there is no movement of data in both the direction, or there are no multiple outputs that are generated from the data flow node. This is a normal sequence what you people can write. For example, if I give you a logic design equation or a logical equation, y is equal to x into a plus y into b, you people will be able to write down the circuit diagram with respect to this particular equation, right? The circuit diagram, whatever you are going to write here, that can also be compared very similar to the data flow graph model itself. One of the simplest ways in which you can represent a process, or one of the simplest models that do exist among all the other models in order to for the selection purpose. So initially, whenever a designer goes with the design process, he will normally be selecting DFG model itself. So this is regarding the first one. Second one is the advanced one of the DFG, which is called as CDFG. So in the CDFG model, it is basically a model which will work based on the conditions. It's given here. In the DFG model, the execution is controlled by the data and it doesn't involve any control operations. Whereas in the CDFG model, which is used for the modeling applications, it involves conditional program execution. So your data will get executed, or the inputs will undergo a particular operation only if a specified condition is satisfied in case of your CDFG. Whereas in case of your data flow graph model, there were no conditions. You used to simply give the input and it used to produce the output. Whereas in case of your CDFG, there are conditions. Sir, how does the condition look like? The condition looks like this. If flag is equal to 1, then you go with the process. X is equal to a plus b and y is equal to a minus b. Suppose if flag is equal to 0, suppose if flag is equal to 1, then this condition or this instruction gets executed. Suppose if flag is equal to 0, the second condition gets executed. How do you actually represent this, or how do you graphically represent this? That is represented using a diamond block. Diamond block is nothing but a decision making element or a decision making block. So inside the decision making block, you write the condition and you check whether the condition is true or false. If it is true, you write a particular equation, and if it is false, you write other equations. See, check here. If flag is equal to 1, if it is true, A and B are the two inputs, it gets added up here, and the output of A plus B, or the data flow node, goes to the output. Suppose if it is false, A and B are the same inputs, but they get subtracted. That is, A minus B will happen, and that will also come to the output. Remember here, at a time there cannot be two outputs. There can be only one output at a particular time. This is what is meant by your CDFG model, which we have in fact discussed in the previous video session also. Moving on further, or moving on to the complex models what exist in the design of an embedded system. The first one is called as state machine model. In fact, the state machine model, you people have already studied in your analog and digital electronics in the very last part of your 5th module. You have studied this. So basically, what is the state machine model? State machine model is actually a model which will be reactive, or even which is actually used for event driven or reactive embedded systems. So what do you mean by this reactive or event driven embedded systems? For example, let us say that if A plus B happens, only then the next condition or next execution starts place. Always B minus C happens, then the next instruction gets executed. So this is what is meant by event driven. Only after execution of a, or only after happening of a particular event, the next event will take place. If this event doesn't take place, this event will also not happen. That is what is meant by reactive or event driven embedded system. So normally if your embedded system is reactive, or if your embedded system is event driven, then normally this model will be handy in order to represent them. Normally your state machine models will be describing the system behavior using 4 terminologies. One is called as state, other one is event, actions and transitions. So normally a model or a system or an embedded system will be represented using 4 terminologies here: state, event, action and transition. What is actually a state? A state is a representation of a current state, current situation. What is an event? Event is an input to the state. What is transition? Transition is the transition from one state to other. Action. Action is the activity that is performed by the state machine if a particular event happens. So that is how you represent a FSM model or state machine model. Normally, when you take a particular embedded system, there will be finite events happening, right? There will be finite number of events happening. So normally you can call this particular model as FSM model also, finite state machine model, because normally in case of any embedded systems there will be no infinite events. There will be only finite number of events happening, and that is why we can call it as finite state machine model also. So if you want to represent a system using FSM model or SM model, you need to know, you need to be knowing what are the events that are happening in the system, what are the actions that are happening in the system, what are the states of that particular system, and what are the transitions that happens in that particular system. If you know these three or these four things of a particular embedded system, then probably you can represent a system using a FSM. For example, if the things are not clear with you people, let's take an example here. Let's take an embedded system for a driver passenger seat belt warning in a automobile using FSM model. Or let's take this example. So normally you know that if you have a car, there will be a seat belt. So as soon as you ignite the seat belt, ignite the engine, your seat belt will start giving an alarm, right? And that alarm will continue for around 5 seconds or 10 seconds, and after 10 seconds it will go off, isn't it? So that is an embedded system here. So that has been explained here in detail, and we will be representing that seat belt mechanism of a passenger automotive system using an FSM model. See, how does this work? When the vehicle ignition is turned on and the seat belt is not fastened within 10 seconds of ignition on, the system generates an alarm signal for 5 seconds. The alarm is turned off when the alarm time expires, or if the passenger fastens the belt, or if the ignition switch is turned off. This is what it happens, right? So you turn on your car and suddenly you will be getting an alarm. And once you start getting an alarm, if you want that alarm to go off, you should either fasten your seat belt, or you should either turn off the engine, or you should wait for 10 seconds, because normally that alarm will ring for around 5 seconds or 10 seconds. But nowadays what is happening there is it will be continuously beeping until you fasten the seat belt or until you turn off the ignition. So this particular system has to be represented using an embedded system, or this particular system of an embedded system should be represented using an FSM. As I said you, if you want to represent a system using FSM, I need to know the four terminologies. That is, I need to know state, I need to know event, I need to know the transitions, and I need to know the actions. So here, the states of a passenger seat belt warning system are alarm off, waiting, and alarm on. And the events are ignition key off, ignition key on, timer expire, alarm time expire, and seat belt on. So we know what are the states and what are the events of this particular system. So alarm off, waiting, and alarm on are the events. They are the main things. And states. The events are ignition key on, ignition key off, timer off, alarm time expire, and seat belt on. So these are the events. So let's check out how do you actually represent them. See, here it has been represented. Using FSM, the system requirements of a seat belt system can be represented here. So here you have the states. The states are given here. This is your state. Alarm off is one state, waiting is one more state, alarm on is one more state. And the events that are happening is your alarm is off. You will turn on the ignition key. Once you turn on the ignition key, the system will wait for 5 seconds. The system will wait for 5 seconds. And after waiting for 5 seconds, what it will do is, it will turn on the alarm. As soon as the timer expires, the alarm will be turned on. And the alarm will be on until the alarm time expires. So once the alarm time expires, your alarm will go off. Suppose your alarm is on and you have turned on the key and your system is in the waiting state. Your system is in the waiting state. Then if you want the alarm to be turned off, what you can do is, you can either fasten the seat belt or you can either turn off the key. So these are all the events that are happening. These are the events that are happening which are transiting the states from one state to the other state. So from waiting state, it will wait for some time. And as soon as that waiting time is over, your alarm will be on. And that alarm will remain on until the alarm time will expire, or you turn on the seat belt, or you fasten the seat belt, or you turn off the ignition key. So this is what is your FSM representation, where you will have states, you will have events, you will have transitions, and you will have action that happens. Action that is happen. Actions are not represented in the FSM. So this is how it works. In fact, this particular system, that is LRM on, this itself can be modeled as an FSM. That itself can be modeled as an FSM, and if you are going to model that FSM, normally that LRM will have an idle state, ready state, and running state. So idle state, if it is an idle state, if it has to go to the ready state, what should happen? Model should be the model should be loaded with the, or the state should be loaded with the timer. One second. And after the timer has been loaded with the event, your state will be ready. As soon as the state is ready, it will wait for some time and it will run the alarm. Your alarm will be on. So it's given here. The alarm on state continues until the seat belt or the ignition key is off. This is for the previous one. The wait state is implemented using a timer. The timer also has a certain set of states and events for the state transition. Using the FSM model, the timer can be modeled as shown in the following figure. So using the FSM, the system requirements can be modeled. See here, as seen from the FSM, the timer state can either be in the idle state, ready state, or in the running state. During the normal mode, when the timer is not running, it is said to be in the idle state. Well known things. The timer is said to be in the ready state when the timer is loaded with the count corresponding to the required time delay. The timer remains in the ready state until the start timer event occurs. The timer changes its state to running from the ready state on receiving the start timer event and remains in the running state until the timer count expires on the start timer event occurs. So what you can do is, you can actually look into this particular model and you can explain the things. So these are the three states. When the state starts transmitting from one state to the other state, and which event will be making it transit from one state to the other. So if it has to move from the idle state to the running state, the event that should happen is the timer should be loaded with the timer count, and the action what will happen is your timer will be getting loaded with the new count. And if it has to move from the ready state to the running state, the event that you should do is you should start the timer. Once the timer has been started, the action that will happen is the count will go on decreasing. If it has to move from running state to idle state, the event that should happen is you should stop the timer or the timer should expire. The action that will happen is set timeout flag or timeout interrupt. So this is how you can represent any system using a FSM. Any particular system can be represented using an FSM. Very similarly, we have one more example to be taken here. There are a lot of examples which are given in the textbooks. You can refer them. So this is one more example of a coffee vending machine. So normally what happens in the coffee vending machine is the person will be inserting the 5 rupee coin, and once the 5 rupee coin is inserted, the machine will be waiting for the instruction from the user whether he wants coffee, tea, or he wants to cancel the order. Suppose if he cancels the order, the 5 rupees will come back. Suppose if he orders for a tea, the tea will be disposed. Suppose he orders for a coffee, the coffee will be disposed. See, the coffee vending machine has been represented in the using an FSM model here. See here, state A, wait for the coin. So once the coin has been inserted, state B, that is wait for the user input. What will be the user input? If the user asks for the tea, tea will be dispensed. If the user asks for the coffee, coffee will be dispensed. Suppose here if the user cancels the order, then the coin will be sent out and the machine will go back to the state A itself. That is how you can represent a coffee vending machine. You can look into this in detail and you can learn into this, or you can learn how basically the actions are all copied, or what are the actions, what are the states, what are the different transitions that are happening in the particular embedded systems. Moving on further, that has been explained here. All the things has been explained here. Whatever I told you right now has been explained here. One more example what is given here. I am not going to explain this in detail here. This is with respect to your, I don't know how many of you are aware of a coin, 1 rupee coin box. 1 rupee coin box in which you can call your friend and you can speak to him for some 60 seconds. So that has been explained here. This is comparatively bigger one which has got multiple states. There are multiple states in which the phone is in the idle state, the call is ringing, and they'll be waiting for the coin, waiting for the number, dialing, and 45 seconds will happen. There should be a beep happening. So everything has been explained here with respect to your FSM. And don't worry, they are not going to ask you, or they will not expect you to explain such a complicated example in the exams. They, in case if they ask you, they will either ask you a coffee vending machine or they will ask you a seat belt warning embedded system to be represented in terms of a finite state machine model. So kindly learn coffee vending machine and the seat belt warning system in detail and try to explain every states, every event and every transitions that happen within the systems. This is regarding the third way in which you can represent a model. This is comparatively easier. Normally any person, if he goes and looks into that, he will come to know, okay, this is what I need to do and this should be doing this particular functionalities. That is how you actually design a system. So initially you took a data flow graph model. After that you came to know that there should be some control things that are happening. So control data flow graph model has been taken. After the control data flow graph model, you try to uh, break down the entire functionalities into sub functions. That is what happened in case of your FSMs. See here what is given us, there are some time state machine models which translates the requirements into sequence driven program, and it is difficult to implement the concurrent processing with FSM. What he is saying is, there are, let me say, there are some five tasks to be performed by a embedded system. So I need to write the first task, second task, third task, fourth task and fifth task, and I cannot make sure that first task will happen, second task will happen second, third task will happen third. You cannot write an FSM which will be saying that, okay, this is a task what is going to happen first, this is a task what is going to happen next. So in case of those systems you cannot employ a finite state machine model. In case of that you need to go with the hierarchical or concurrent finite state machine model, which is called as HCFSM. In fact, this is an advanced version of FSM. Here it extends the conventional state diagrams by and or decomposition of states together into interlevel transitions and broadcast mechanisms for communicating between the concurrent process. So if you say that, sir, I want the first task to be performed separately, so I will write this as a separate FSM. If you want the third task to be performed second, I'll write this as a separate FSM. Then I'll try to interconnect them. This is what is called as HCFSM. Just an introductory part which is given to you. If somebody asks you, sir, what if FSM doesn't work, or what if I have a sequence like this is what it has to happen first and this is what it has to happen next. So normally you can go with the HCFSM model. This is the third one. Sequential program model. Sequential program, I need not explain it to you at all because this is the way in which you are going to write a program. In sequential programming model, the functions or processing requirements are executed in a sequence. It is same as the conventional procedure programming in the way in which you are going to write. Here the program instructions are iterated and executed conditionally, and the data gets transformed through a series of operations. FSMs are good choice for sequential programming and modeling. This is the normal way in which you are going to write a program. You write a C program, right? That will be a sequential one. You know what has to be printed first, what has to be printed next, what has to be printed later. And at the max, what you can do is you will be writing a flowchart for that. So you can represent your sequential program either using a FSM, or you can either go with the flowcharts also. If you're asking me, sir, how do you actually write that particular sequential program, or how actually it is going to look like? So what we'll do is we'll take the same example and we'll check the way in which the program is to be written for that. See here, first of all, I'm defining the terms. On is 1, off is 0, S is 1, no is 0. After that, function void, seatbelt warning. When should the seatbelt warn? First of all, wait for 10 seconds. During the waiting for 10 seconds, you need to check whether the ignition key is on, and you need to check whether the seat belt is off. And after, if both the conditions are done, you need to set the timer and start the LRAM. When you are starting the LRAM, you need to keep on checking whether the seat belt is off, and check whether the ignition key is off, and check the timer is on. Suppose if any one of this condition doesn't get satisfied, if any one of this is not true here, then you should stop the alarm. This is how you write a normal program, isn't it? This is how you write a C program. And this C program can be transmitted into a flowchart like this. Ignition key is on, you'll be waiting for 10 seconds. You'll be waiting for 10 seconds. And again, you'll be checking whether the ignition key is on. If the ignition key is on, you'll be checking whether the seat belt is on. If the seat belt is fastened, you go to and you stop the process. If the seat belt is still not on, you set the timer in the alarm for 5 seconds. And after setting that alarm, before turning on that particular timer, you again check whether the ignition key is on. If the ignition key is on, you check whether the seat belt is on. And if the seat belt is not on, then you check whether the timer has expired. If the timer has not expired, you go on checking the things for every decrement in the timer. This is what it happens in case of your sequential programming. Normally this is called as sequential programming. Okay, the thing what I have written here, this is called as sequential programming. The normal way in which you are going to write your C program. Nothing else. It's a proper sequence. What should be checked first? If that condition is satisfied, what should be done next? If that condition is satisfied, what should be done next? If that is not satisfied, what else should be done? Until when this condition has to be satisfied. That way of writing a program using a particular course, you call that particular method as sequential programming. This is one more method. This in fact is one of the complicated one, concurrent communicating process model. Concurrent communicating process model is all about breaking the task, breaking the entire bigger task into smaller tasks. See here, sequential execution leads to single sequential execution of task and thereby leads to the poor processor utilization when the task involves input, output, waiting, sleeping for a specified duration. Very true. When you are going to check for the ignition, if the ignition is turned on and if you are going to check for the timer, I do not need a system will be checking the ignition again. So I need to have a system which will be checking only the timer. After the timer has been checked, then I need to have a system which will be checking the ignition. After the ignition checking has been done, I need to check whether the seat belt is on. You are getting the sequence, right? When you are checking whether the ignition key is on or whether your seat belt is turned on or whether your timer has been set, it is only a single system which is going to work at a time. It is not that all the systems will be working at a time. So concurrent by communicating process model is going to break down the entire process into smaller tasks, and the smaller tasks are interconnected or they are communicating with each other so that your processor can be utilized to the maximum. For example, let us say I need one processor to check the ignition and one processor to check the timer and one processor to check the seat belt. But all these three processes doesn't happen together at a time, right? So what they do is they use a single processor, and using a single processor they give the work to that single processor so that your processor will not be underutilized. See, it's given here. If the task is split into multiple subtasks, it is possible to tackle the CPU usage effectively. When the subtask under execution goes to wait or sleep mode by switching the task execution. Suppose if that processor is not checking the ignition on, I can ask that processor to check whether the seat belt has been fastened, or I can check that processor to check whether the timer has been set. So it normally means that it is concurrent. A single person is going to do the multiple tasks. This is what happens in case of your concurrent processing modeling. If you take the example of a seat belt, same example has been taken here. We can split up the tasks into timer task for waiting 10 seconds, task for checking the ignition key, as I said you, task for checking the seat belt status, task for starting and stopping the alarm, task for alarm timer or alarm timer task for waiting 5 seconds. So all these tasks are done by a single person. Always what I should have done is I should have taken 5 processors and every processor would be doing this particular task. Whereas in case of your concurrent communication model, you take a single processor and the single processor is going to handle all this particular task. We have 5 tasks here and we cannot execute them randomly or sequentially. We need to synchronize their execution through some mechanism. That's what I said. I need to have some mechanism through which the tasks will be handled by a single processor at a time. See, here it's given. Create and initialize events. This is how it is actually going to be written. Wait timer expire. This is one task. Ignition on. Second task. Ignition off. Third task. Seat belt on. Fourth task. Seat belt off. Fifth task. Alarm time start. Alarm time expire. So there are normally 7 tasks to be performed. See, what you do is you create a separate tasks here. Create task wait timer, create task ignition key status monitor, create task seat belt status monitor, create task alarm control, create task alarm timer. So you divide the tasks into multiple tasks or subtasks and you ask the same person to handle that. Because I am pretty sure that all the tasks are not going to be performed randomly or at a time. It is one by one. It is going to be executed sequentially. So that is what happens in case of your concurrent models. This is the fifth one. So it's given here. Every task has been splitted up. This is a task for wait timer. This is a task for ignition monitor. This is a task for alarm control task. This is a for seat belt. This is for again alarm to start and sleep. So every task has been split up here, and they have their own sequential programs here. They have their own sequential programs which are written here. So every task has been split up here. So what we had previously was we had one single program, but right now we have split up the tasks into multiple programs, and every subtask has been assigned to a single person, so that your processor is not underutilized. This is one more important method. Last one, which is called as object oriented model. Object oriented model is actually a copy of the concurrent model itself. So in case of previous one, you divide the task into subtask. But in case of your object oriented model, instead of calling this as subtask, I'll be calling this as object. See here, the object oriented model is an object based model for modeling system requirements. Yes, it disseminates a complex software requirement into a simple well-defined pieces called objects. So simple well-defined pieces means subtasks, and every task is pretty much clear what is going to happen and what are the works that are happening in this particular subtask. Object-oriented model brings reusability, maintainability and productivity in the system design. As I said you, a single person is going to perform the task, which means that I'm going to reuse that processor again and again. In object-oriented model, object is an entity used for representing or modeling a particular piece of a system. So when I say that it's a particular piece of system, this is nothing but a event that should happen in a particular embedded system. Each object is characterized by a set of unique behavior or state. A class is an abstract description of a set of objects, and it can be considered as a blueprint of an object. So this is what it should happen. A class represents the state of an object through member variables and object behavior through member functions. And this member variables and the member functions can be public variables and public functions, or they can be like the protected variables and functions. If it is public variables and functions, anybody can access it, whereas if it is protected variables and functions, the access is denied. Only the people who has got the permission to access them can access it. So when I say it is accessing, it is about making that particular task happen. So here every task has been subdivided and every task is called by the name object, and every objects are interconnected using the class. They are connected using a class, and that class represents the state of an object through member variables and the object behavior through member functions. So they are interconnected using the classes, and the classes, whatever they are going to interconnect, are nothing but the variables or the behaviors that exist in a particular system. So this is regarding the various models that has been employed in the designing of an embedded systems. If you are asking me, sir, which is very important for us or which one should be studied here, probably for you people, sequential modeling and FSM are the two important things what you need to concentrate on, because they will normally be asking you to represent a particular system using FSM, or they might ask you to write a sequential program for a particular task. So if it is concurrent, you need to divide that particular program into subtasks. Object oriented program means it is all about dividing the tasks into objects and interconnecting them via the classes. So you need to go through this, in fact through the notes as well as the PPT what has been forwarded to you people, and you will get a very clear cut idea regarding what exactly are the different models and how are they varying from each other. So this many things you need to be studying, or this many things has to be known by you people. As I said, you two are really important from the examination point of view. Anyways, thank you.